Time for another lecture, our last today, our last for this conference. Scowcroft, adjoining a strong unit to a hyperarchimedean lattice-ordered group.
Thank you very much, Chip. I'd like to express my gratitude to Chip and Jim for working to maintain the tradition of OAL-RAG meetings after a long gap for which nobody was really responsible. I hope you'll all join me in thanking them for their hospitality. My subject today is when one can adjoin a strong unit to a hyperarchimedean lattice-ordered group, thereby remaining hyperarchimedean. All right, well, you've already heard about lattice-ordered groups, which I'll call L groups. I mean, they are, Brian was talking about vector lattices. Here you just don't have the real multiple scale multiplication. You've also heard about Archimedean vector lattices, Archimedean L groups are defined in a very similar way. And these are always abelian as groups. So in what follows, all the L groups I'm talking about will be abelian. Now, an L group is said to be viewed as a structure where you have the group operations and lattice operations, and the identity of the group is said to be hyperarchimedean, just in case all of its homomorphic images are Archimedean. Of course, in the world of linearly ordered groups, Archimedean and hyperarchimedean are the same, but they are different here. So, for example, any direct sum of copies of the real numbers will be hyperarchimedean. However, if you take a direct power of infinitely many copies of R, that will be Archimedean, but it will not be hyperarchimedean, because given any, roughly speaking, given any function in R to the I, you can get one that grows much more quickly. Now, there are a number of different conditions equivalent to being hyperarchimedean. I'm going to tell you about some of them, just because some of these they don't mention. You don't have to refer to other L groups in these conditions. So here are some conditions equivalent to being hyperarchimedean. Number 2 says that whatever element of the group you pick, you can split the group into 2 convex sub-L groups in a special way. Now, what are these sub-L groups? G of A is what, roughly speaking, what Brian called brackets A. So it's the smallest convex sub-L group that contains A as an element. And it turns out it's the set of all elements bounded in absolute value by multiples of the absolute value of A. What is absolute value? Well, it's defined in a natural way as A joined minus A. And in an L group like C of X, that is the continuous real valued functions on the topological space X, that definition of absolute A will give you what you think it should. The absolute value of a function. So that's G of A. A perp is the set of all elements. Well, again, something like this appeared in Brian's talk. Set of all elements, as we say, disjoint from A, meaning that the absolute value of this element meet the absolute value of A is 0. And in C of X, these would be elements whose supports, functions who support are disjoint from the support of A. Another condition is that for all non-negative A and B in G, there's some natural number n so that A meet NB is A meet n plus 1B. Again, conditions 2 and 3, they just refer to the group, the L group G. You don't have to talk about other L groups in the relationship to G. However, some of these other conditions are very convenient. For example, one that is I found very convenient when trying to show that a given L group is hyperarchimedean is the condition that every linearly ordered homomorphic image should be Archimedean. So then you can use what you know about Archimedean linearly ordered groups, which are, of course, isomorphic to subgroups of the real. Now, if we take any L group you can look at the set of all these, what are called principal convex sub-L groups, all these L groups, sub-L groups of the form G of A. And if you partially order that collection by inclusion, you always get a distributive lattice. However, it turns out another condition of being hyperarchimedean is that this distributive lattice is what's called a generalized Boolean algebra. And that is, roughly speaking, a Boolean algebra, perhaps without a top L. Another word for it is a relatively complemented distributive lattice. So you have a distributive lattice, and then for two elements, you have what in the sort of Boolean interpretation would be the set periodic difference of the elements. And there are axioms you can write down to axiomatize that. They also correspond to Boolean rings. But again, Boolean rings possibly without an identity element, a multiplicative identity. And I'll use all these terms interchangeably, though of course from the universal algebraic point of view, you should distinguish these categories. But and one thing to notice that if you have a generalized Boolean algebra D that is not a Boolean algebra, so it corresponds to a Boolean ring without a unit. Well, there's a canonical way to take a Boolean ring without unit and adjoin to it a unit, so you get a Boolean ring, of which the thing you started with is a maximal ideal. Any two ways of doing that, well, starting with your generalized Boolean algebra will be isomorphic over it. So we have these. An L group will be hyperarchimedean just in case this distributive lattice corresponding to it is a generalized Boolean algebra. Possibly without you. Now, if you have an L group, an element of the L group, that element is called a strong unit. I think this came up in this talk, just in case it is non-negative and its natural number multiples are cofinal in the group. So for example, the constant function value 1 in C of X when X is compact. However, when X is not compact, 1 needn't work. So in C of R, there is no strong unit. Again, because given any real value continuous function on the reals, you can concoct another one that grows faster than any natural number multiple of that function. Now, I will use the term unit for strong unit here, because as it turns out, if you go back and look at condition 2 of the equivalent conditions for hyperarchimedean, right, what we heard in Brian's talk of weak units are the same as strong units in the hyperarchimedean. Now, when G is hyperarchimedean, it will turn out that G has a unit just in case this distributive lattice corresponding to it as a top element. So just in case this distributive lattice connected with it is a Boolean algebra. Now, Tony Hager and I worked on the following question. When you have an Archimedean L group, when can you embed it in an Archimedean L group that has a strong unit? And we use topological and algebraic methods to answer this question, you know, to a certain extent. I became interested in the analogous question in the hyperarchimedean context. So I'm interested in the question, if you have a hyperarchimedean L group, when can you embed it in a hyperarchimedean L group with strong unit? Now here I'll let HA be the class of hyperarchimedean L groups and EHU be the class of hyperarchimedean L groups that can be embedded into ones with unit. Now, of course, the basic result here is that these are different classes. There are some hyperarchimedean L groups that cannot be embedded into hyperarchimedean L groups with unit. And the first example of this was obtained by Conrad and Martinez paper, I think in 1990. And in fact, their example has an even stronger property. They have a hyperarchimedean L group that cannot be embedded into an Archimedean L group with strong. about 20 years after the Conrad Martinez paper, Hager and Johnson find the techniques of Conrad and Martinez and came up with some other examples of hyperarchimedean L groups that could not be embedded into one unit. And then some years after that, I came up with yet a different kind of example. So these classes are different. Another thing to notice is that even when you can embed a hyperarchimedean L group into one with the unit, there's no canonical way to do it in general. So it turns out that if you take a hyperarchimedean L group that can be embedded into one with the unit, but this hyperarchimedean L group is countable and divisible, then in fact there are uncountably many ways of adjoining a unit to it. Pairwise non-isomorphic. And these new hyperarchimedean L groups are generated over the old one just by adjoining a unit, closing under the group and lattice operation. And they're also essential extensions. So you're not taking the direct sum of this original L group with something else that really has nothing to do with it. Every ideal in the non-zero L ideal in the top order will have non-zero intersection at the bottom. So they're closely related. And this is analogous to results that Tony and I obtained for the more general question about Archimedean. My proof of this in a paper I published on the subject has a slight error, which if any of you ever look at the paper, you might try to find it. It can be repaired. And so the proof essentially works, but there's a slight error. Okay, so not every hyperarchimedean L group can be embedded into one with the unit. And even when you can do it, there's not necessarily a canonical way to do it. However, it does turn out that if you take any generalized Boolean algebra, it is the distributive lattice associated with something, an L group that can be embedded into a hyperarchimedean L group with unit. It's a simple application of the so-called bounded Boolean powers. So that means that knowing this distributive lattice cannot rule out a hyperarchimedean L group being embeddable one-to-one with a unit. Of course, that result raises the question, are there special generalized Boolean algebras which, if you know your hyperarchimedean L group has this as a distributive lattice, it has to be embeddable one-to-one with a unit. And I will call a generalized Boolean algebra unit embeddable just in case whenever every hyperarchimedean L group G, whose distributive lattice is D, can be embedded in a hyperarchimedean L group with a unit. And of course, if D happens to be a Boolean algebra, it will be unit embeddable trivially. And then the question is, are there others? There are others, these distributive generalized Boolean algebras, which if your hyperarchimedean L group has that as a distributive lattice, it can be embedded in a hyperarchimedean L group with a unit. And it turns out there are some. And in fact, there's a result that's proved by a relatively simple algebraic argument that shows you these exist in profusion. Namely, if your generalized Boolean algebra is disjointly generated, then it's unit embeddable. What is disjointly generated? Well, remember, D is a maximal ideal Boolean algebra. So you can ask what kinds of sets of generators it has as an ideal. So to say it's disjointly generated is to say it has a subset of pairwise disjoint elements such that everything in D is bounded above by some finite join of elements of that subset. That's what disjointly generated means. So for example, if you take any direct sum of copies of the reals, the corresponding distributive lattice is disjointly generated because it's just a corresponding direct sum of copies of the two-element Boolean algebra. And that has, as its disjoint generators, characteristic functions of singletons. And in fact, if you work through that example, take an arbitrary direct sum of copies of the reals. show that that can be embedded into it's hyperarchimedean, show that it can be embedded into a hyperarchimedean unit. If you can do that example, you prove this theorem. It's a more general version. I mean, I shouldn't quiz you on this, but in a direct sum of copies of the reals, what it would be a natural candidate for a strong unit.
Yeah.
The constant function with value 1. So, and it's that kind of an argument that works here. Now, it turns out that countably generated,
Bill, can I ask?
yes,
All right, so I'm envisioning, I take an infinite set and then I take the finite subsets. That's gonna be one of these disjointly generated.
Yeah.
Kind of things. Are there other things that just come like you quickly?
yes, well, any countably generated, generally there's Wesleyan algebra, is disjointly generated.
Okay.
So for example, any countable D will work. Of course, countably generated doesn't mean countable. Because if you took the disjoint, the direct sum of countably many Wesleyan algebras of any kind, that would be countably generated. So anyway, this gives you a lot of examples. Now, given this theorem, though, I found it natural to ask whether there are other examples not covered by it. So are there unit embeddable generalized Boolean algebras that are not disjointly generated? Now, of course, so far we've been talking about, I said there are lots of examples of these Ds that are disjointly generated. So what about Ds that are not disjointly? Well, probably the simplest example of such a thing is what's called the interval algebra on omega 1. So, candidate for something that is not disjointly generated, that might not be unit, is this interval algebra. Now, I'll try to explain what, if you start with a linearly ordered set, it has a corresponding interval algebra. I probably won't explain the term interval, but this is up to isomorphism what interval algebras are. So you take your linearly ordered set, make it into a vector space of the 2-element field with basis A. Okay. Now that's almost a Boolean ring, except you don't have multiplication. So how do you multiply two things together? Well, you take two sums of distinct basis elements. And how do you multiply them together? You take, for each CI and DJ, you take the minimum and you add up all of them. And with that multiplication, you get a Boolean ring. And it's a Boolean algebra just in case the linearly ordered set you started with has a top element, which becomes the unit of the Boolean algebra, Boolean ring. And why are these called interval algebras? I mean, this sort of thing was isolated first by Mostovsky and Tarski in a paper of 1939. Well, it turns out you can represent the elements of this interval algebra I've described as disjoint sums of certain special kinds of intervals in the ordered set. That's where the term interval algebra comes from. And in fact, that representation is sometimes convenient to use. Turns out, though, that if you start with a linearly ordered set that has uncountable cofinality, so no countable sequence is cofinal in the ordered set, then this interval algebra is not disjointly generated. So the interval algebra on omega 1 is a natural, I mean, it's not disjointly generated. And so then the question is, well, could it be unit embeddable? Now, I thought about this question for a long time. I didn't resolve the status of the interval algebra on omega 1, although I have learned something about it that I'll tell you about a little later. But after puzzling over this for a while in the middle of the pandemic, I began to think, well, maybe I should be looking at interval algebra on larger cardinals. And the reason for this is that in my desperation through various sources, I was reminded of this work from the 40s and 50s linking measurable cardinals with certain properties of L groups. Particular discrete space is real compact, if and only if its cardinality is not measured. And that's a topological result, but then you can look, ask what that means about C on the discrete set and so on. Okay, so I began to think, well, maybe I don't look at the interval algebra on omega 1, but I look on the interval algebra on kappa, some kappa bigger than. And here's a definite, there are all different kinds of definitions of special large cardinals. Cardinal kappa is said to be weakly compact, just in case it has two properties. First, it is inaccessible, by which I mean strongly inaccessible. What does that mean? It's a regular cardinal. And if lambda is less than kappa, then 2 to the lambda is less than kappa. So that the combination of those two is inaccessible. And then it satisfies this condition. This is a version of Ramsey's theorem.
Excuse me.
So this kappa arrow kappa 2 means if you take a set X of size kappa and you look at the unordered pair sets of elements of that set X, and you color them, that collection of things in 2 colors, then there's a subset Y of X of size kappa. So if you look at the unordered pair sets of elements of Y, they all have the same color. So it's, I mean, if kappa were omega, you would get a version of Ramsey's thing. But this is for a bigger cardinal, and since you're insisting that the subset have the same size as the original, this is a strong principle. I use this definition of weakly compact just because it was purely set theoretic. But in my work, I've used an equivalent condition that is comprehensible along with model theorists. And in fact, this is where the phrase weakly compact came from. So the cardinal is weakly compact just in case. I'm not going to dwell on this, but I did want to mention a cardinal is weakly compact just in case it's inaccessible. And there's a version of the compactness theorem of first order logic, but for a much more expressive logical system. So if you have a first order language in the sense of model theory, and you have this infinite cardinal kappa, what are sentences of R kappa kappa? Well, you can take conjunctions and disjunctions of fewer than kappa many formulas. And if you have a set of fewer than kappa many variables, you can apply a universal quantifier to it or an existential quantifier to it. Those are the extra operations that have to go from first order logic to this R kappa kappa. And of course, that is when kappa is uncountable, that is much more expressive. If, for example, to say that a linear order is well ordered, you can just write that out in the sense of R omega 1. Okay, but this version of the compactness theorem says that a set of sentences is satisfiable. It's just in case every subset of size less than kappa is satisfied. Why weakly compact? Well, the weakness is that there's a restriction on the size of the set of sentences. Because as it turns out, if the language has size at most kappa, then the set of all R kappa kappa sentences up to kappa is inaccessible is up to equivalence of size kappa. So this applies to theories of size kappa, but not to bigger theories. If you allow this, if you demanded this compactness theorem hold for theories of arbitrary size, you would get what's called a compact cardinal. And, well, for example, all measurable cardinals, not necessarily cubes. If your cardinal kappa is weakly compact, there are kappa many inaccessibles less than. So this is big. I mean, most of us do not encounter even inaccessible cardinals. So even just inaccessible, but then this extra condition makes it Now, using this compactness theorem, so it'll show the following. So if kappa is weakly compact and you have a generalized Boolean algebra of size kappa, which is not a Boolean algebra, then in certain cases, this generalized Boolean algebra is unit embeddable but not disjointly generated. And these are only some of the cases. I have other examples too. But for example, the integral algebra of kappa. That's an example. Or the free algebra, or if the Boolean algebra associated with D is the free Boolean algebra of kappa generators. If the Boolean algebra associated with D is the completion of that previous one. Or if the Boolean algebra associated with B is what's called a saturated, which is a Boolean algebra. Well, if people have questions about what these are, this is the model theoretic notion of saturation. They are saturated, that they are universal and homogeneous. So Boolean algebras of lower cardinal. But anyway, and there's so an axial ideal in this Boolean algebra corresponds to the complement of a point in the stone space. And if you take a special kind of point, again, I can tell you what this definition is later, but you get an example of this theorem where you have something that is unit embeddable but not disjoint generally. Okay, so that's fine for now. I want to go now to a slightly different question. So in these cases, when you have a unit embeddable generalized Boolean algebra, and you have a hyperarchimedean L group whose distributed lattice is that generalized Boolean algebra, you can adjoin a unit and so get a hyperarchimedean L group whose distributive lattice is Boolean algebra. What Boolean algebra is it? So if you have hyperarchimedean L groups, you can embed the distributive lattice associated with the smaller one, G, into the slightly bigger one associated with H in just an obvious way. And so if the original hyperarchimedean L group doesn't have a unit, but the new one has a unit, the distributive lattice associated with G is not a Boolean algebra. The distributive lattice associated with H is a Boolean algebra. Its top element will be H. So that's H of a unit. However, if you look at all the HKs with K and G, that's a copy of G's distributive lattice. And if you take the unit of this Boolean algebra associated with H, and close off the set on the Boolean operations, you get a copy of the Boolean algebra associated with G's distributive lattice. So that's the smallest H's Boolean algebra could be. But it might be bigger. Because in this extension process, you're not just adjoining elements to a Boolean algebra, you're adjoining elements to an L group. And when you combine them in special ways, you may get elements with supports that are completely different from what you already know. So the Boolean algebra might grow in a strange way. Well, my generalized Boolean algebra will be said to be strongly unit embeddable, just in case. If you take a hyperarchimedean L group whose distributive lattice is D, you can embed it into a hyperarchimedean L group unit whose Boolean algebra is as small as possible. Anyway, it's just it's isomorphic. It's generated over the copy of G's distributive lattice in H's Boolean algebra by the top. Now, it turns out if you look at the proof that disjointly generated generalized Boolean algebras are unit embeddable, in fact, they are strongly unit. So you can arrange things so that you go to hyperarchimedean L group with a unit, and the Boolean algebra you get is as small as possible, generated over the old distributive lattice by the top element. Then the question is, what happens to these examples from my last theorem when I use weakly compact cardinals? Roughly speaking, the first three examples go through. So the interval algebra, when kappa is weakly compact, we have a generalized Boolean algebra size kappa that isn't a Boolean algebra. Well, if we look at the interval algebra on kappa, that is strongly union. Well, if the associated Boolean algebra is the free Boolean algebra kappa free generator, so that is strongly union. If the associated Boolean algebra is the completion of that, that's strong union. How do you prove these results? Well, the proofs are more complicated versions of the previous proofs, but so you use this model theoretic compactness theorem. Plus, you have to use some algebraic information. There are certain embeddings of Boolean algebras admit retractions. And notice that the fourth set of examples about certain kinds of saturated Boolean algebras, that isn't here because in that context, these retractions need not exist. It's not clear how to proceed. So the first three cases listed on the last slide, they can be established by an elaboration of the previous argument, but where you have to that you exploit the fact that some of the Boolean algebras you're betting on do not can retract the top one. This method doesn't seem to apply in the saturated Boolean algebra case. At one point, I thought I had established it by using, and again, this jargon phrase will mean something only to people who know something about model theory. By using an emitting types argument. Because if you study the conditions of unit embeddability and strong unit embeddability carefully, the former is one that should be established by compactness arguments. The latter one is one that should be established by emitting types arguments. The problem was I could set everything up, and I thought I had an emitting types argument, an emitting types theorem would work, but it turns out the emitting types theorem is false. So it's not true as I originally thought that once you have a compactness theorem, you can do anything. And once you go into uncountable cardinalities with SAR kappa kappa, even if you have a compactness version of compactness theorem, there are certain familiar techniques from model theory that just don't work. It's about unions of chains and so on. It all goes wrong. And so I don't know what happens in that fourth case, whether those are strong. Now, okay, well, naturally, I like these theorems, but one might want to try to get smaller examples. I go up to these weakly compact cardinals. I indicated they are very large. They are so large that you can't prove their existence in an ordinary set. So the statement that they exist is thought to be consistent with ordinary set, but you can't establish their existence. You can't establish the existence of ordinary set theory, even of inaccessible cardinals, not alone with weakly compact. So there's, of course, some reason to want to reduce kappa. And also, of course, even if you reduce kappa, the question is, what about the interval algebra on omega 1? The interval algebra on 2 to the aleph 0. What are these? What can we say about them? Well, okay, I was able to show in my work on I omega 1 that the interval algebra on 2 to the aleph 0 is not strongly union. How did I do that? Well, I built an L group whose distributive lattice was the interval algebra on 2 to the aleph 0. It can be embedded, it's hyperarchimedean, it can be embedded in hyperarchimedean with a strong unit, but you have to blow up the distributive lattice to Boolean algebra is too big. Of course, that still doesn't settle the question about the interval algebra on omega 1 unless we assume the continuum hypothesis. However, it turns out that you can't prove in ordinary set theory that the interval algebra on omega 1 is unit compatible. Now, of course, a result like that immediately suggests, well, why not just show it's not unit? That's the temptation of lurking in the background. But how do we establish that you can't show in ordinary set theory that the interval algebra on omega 1 is unit compatible? Well, this rests on an independence result. Namely, you can expand ordinary set theory by different principles that are known to be consistent with ordinary set theory that give you different answers. So let script C be the collection of all sub-L groups of the continuous real valued functions on omega 1. Omega 1 is given the order topology. And it turns out that when you give omega 1 the order topology, if you look at the compact open subsets of omega 1, they give you a copy of the interval algebra using one of these representations of interval algebras as collections of unions of intervals. So I looked at sub-L groups of C omega 1, which are hyperarchimedean. And if you look at the supports of elements of this sub-L group, it's all the compact open subsets of omega 1. It's this copy line. But the principal convex subgroups of these sub-L groups are all smaller than continuum. Okay, so this is a certain collection of hyperarchimedean L groups. It is non-empty. There are such things. If you look at the sub-L group of C omega 1 generated by characteristic functions of compact open subsets of omega 1, that forms C. Okay, so they're definitely in ZFC, the script C is a non-empty collection of hyperarchimedean sub-L groups of C omega 1. However, if you make certain extra assumptions, you get different answers to the question, is C contained in EHU? Is every element of script C embeddable into a hyperarchimedean strong unit? If you assume the cofinality to the L of 2 is bigger than L of 1, then every L group in script C can be embedded in a hyperarchimedean L group unit. In ordinary set theory, you can always, for infinite kappa, you can show that the cofinality of 2 to the kappa is bigger than kappa. So for example, the cofinality of 2 to the L of 0 is uncountable. But unless you make certain extra assumptions, you don't know what it is. So to say it's bigger than L of 1 is a strong way of negating the continuum hypothesis. Because if you have a continuum hypothesis, 2 to the L of 0 equals L of 1, which is a regular cardinal, so that's cofinality 1. This is saying it's bigger than 1. So 2 to the L of 0 could not be L of 1, case 1. However, if you make a contrary assumption called diamond, and that is a strengthening of the continuum hypothesis that is true in Gödel's constructible universe, then there are L groups in C that cannot be embedded into hyperarchimedean L groups. It's not needed. And the subtheory behind these results is all the fact that the statement cofinality to the L 0 is bigger than L of 1 is consistent with ordinary set theory. That was established in the 60s. It's diamond principle, isolated by Jensen, but it's isolated in the late 60s, early 70s. So that's all, but the application to L group seems to be new. Well, there are many questions that remain open. If you have any questions, I'd be happy to answer. So thank you very much.
Questions?
In this theorem, part 1, when you're showing using this extra information, you're showing that that all the guys in C are embeddable. What methods are you using to get that? You're not using compactness.
Well, what this using facts about the definition of C, cofinality to the L 0 bigger than L of 1 implies that there is if you have if you take a G in C, if the cofinality of 2 to the L 0 bigger than L of 1, there's a constant function that is not in G. That's how you use this. I mean, you estimate I'm sorry. Well, yeah, there's a constant, it's cofinality of 2 to the L 0 is bigger than L of 1. Then there's a real number that is not in the range of any element of G. And if you join this corresponding constant function to G, that can serve as a unit, and then you get types of these hyperarchimedean. And what are the results? I mean, where might that come in? Well, the collection of ranges of elements of G. Remember, the elements of little g's, they're all functions from omega 1 to I. Well, each one of these belongs to one of these principal convex sub-L groups, and they all have size less than the L of 0. And the supports of these little g's are compact open sets in omega 1, so they're countable. So the ranges of all these guys are countable. Then take the union of the ranges. Well, the collection of ranges of a GG is less than 2 to the L of 0. And you begin to exploit those facts, and you'll end up the union of all the ranges cannot be, the cardinality is too small. So that's where it comes in, roughly speaking.
What is the diamond does it bring meeting types? So meeting types. I mean, there's this what she's talking about meeting type serum on the diamond. There's not the meeting type. I was just wondering if this is kind of why this diamond is here.
I'm not sure, because I think I would have to check the reference in Hodgett. I think that if you have diamond, the number of types you can emit, the ordinary emitting types theorem goes up, possibly. Because maybe thinking of different as well. But no, I'll have to check that.
I don't know this very well. I was just thinking, it's mentioned that the meeting type serum goes away. But I don't remember the size of this type. Under diamond, comes back.
I mean, the result I was thinking of was the combination of Martin's axiom and 2 to the L of 0 with the L of 1. That allows you to extend the emitting types theorem. So you can emit more types, but in my use of the emitting types theorem, that was to, in this other context, that was to show a strong form of unity. And so, I don't know, I'll have to look this up, but it's relevant to the theme in a different way.
The other issue was about if you were in infinitely languages, I might say it's not an option, but maybe it's great. In these infinitely languages, this hyperarchimedean groups become expertized.
Yes.
So when generalized Boolean algebras, so I could take ultra powers of this, and then allow it to know any of those. So in the infinitary, is there an infinitary version of the Chan-Kissler theorem, which makes this Boolean algebra what you want kind of saturated.
I'd have to check that out, but the ultra product construction works well if kappa is measured. But that would be already an interesting case to look at, because I can,
The fact that this hyperarchimedean become elementary in this language, does this have any impact on?
well, I mean, you need to use an ultra power construction in the context where the ultra power construction preserves these kinds of forms. But there's context where they would. So that would, I mean, again, this kappa is not really back but measurable. So thank you.
Anybody else? Well, let's thank Philip again. Another chat on the previous talk, I think addressed to Brian and Warren, maybe? Let's check it out here. Does that mean anything to you, Brian? Do you wanna
Well, I
comment?
think it's somebody else, brain, I'm a brain.
Well, yeah.
Yeah.
You misspelled it, I think.
Oh,
Maybe he's just calling you brainy.
that could be a compliment.
That might be, that first statement. True. I think for C of X, yes, do you guys have a characterization on C of X is SMP? Is it cloak and pi, is it pi ZD?
Well,
Maybe I should just wait for you to say.
yeah, let's see, I'm just trying to remember, yeah, it's something, we do, oh wait, pi ZDs. No. I mean, sorry, I'm thinking of the other results for FST.
C of X, SMP.
Yeah, SMP, no, I'm not sure off the top of my head,
Okay.
I think it might be equivalent to total pockets.
There's an addition.
Right.